Hayalperestlerin, risk alanların, denemekten korkmayanların cesaretinden doğduk. Bizi asla yarı yolda bırakmayan o sesin rehberliğiyle ilerlemeye ve öğrenmeye devam ediyoruz. Bunun için varız. Bu yüzden gece geç saatlere kadar lambalarımız sönmez. Elveda demek hem hüzün hem de gurur verir. Her şeyi sorgulayarak ve merakımızı besleyerek, dayanıklılığımızı test ederek, sınırlarımızı aşarak, ilerleyerek ve yeni ufuklar açarak yeni bir yol buluruz. Yeni icatlar çıkararak, kendi yolumuzu çizerek. Burası fikirlerin doğduğu ve yeni fikirleri doğurduğu, bizim de doğduğumuz, birlikte büyüdüğümüz ve yükseldiğimiz yer. Burası Yakın Doğu Üniversitesi.
Hello everyone. I would like to welcome again everyone for Room 1 Session 2. We'd like to continue what we started in our first session. So we'll start this session. I would start by calling our presenter, Natasha, that will be presenting a paper titled The Predictive Model for Water Probability. Yes, Natasha. Please.
Hello, can you hear me?
Yes, please just raise your voice a little bit so we can hear you a little bit.
Okay. Thank you so much. My name is Natasha Sonase. I'm a research assistant in the Operation Research Center in Healthcare in Near East University. So today I will be talking about the predictive modeling of water potability, whereby we will be training and testing machine learning models using physical and chemical attributes for the water quality assessment. So to start with, it is what we all know regarding that the earth is made of two-thirds of the earth is made up of water. So it's not that surprising that it's not that all the water that we use on our daily basis. So it will be surprising that only 3% of the water among the two-thirds of the water on the earth are only made of fresh water. And among the 3% of fresh water, only 1% is easily accessible as fresh water, mostly through lakes, soil moistures, water vapor, water in living things, and even rivers. So as we have a large quantity of water, but we still need clean water that we can be consuming on our daily basis. So during this presentation, we are going to learn about what is water quality, how and why do people measure water quality, and we will see the methodology we use to get the water potability in this study, and we represent the results as well as the conclusion. So to start with, the water quality gives us the chemical and physical as well as the biological characteristics of water. So there are many standards set by WHO and UN so that we can have clean water to consume and use on our daily basis. So mostly one of the reasons that we need to do the water quality assessments is the poor water quality, which is mainly got from the water pollution due to climate change and even over-exploitation, mostly in these developing countries. There are many industrial activities, overpopulation, even too much fishing in waters or even seas. So why do we need to measure the water quality and how do we do that? One of the reasons is we set the water quality standards so that you can know if we can even swim in water. You understand? Because most of us like swimming, fishing. So all those are safe to know if we have safe water for you to be able to go to swim, or if the water is safe for the aquatic animals to be able to survive. And the most importantly is the water we use on our daily basis, which now brings out to our main aim, which is portability. So when water is not safe, there are many waterborne diseases recorded worldwide, where millions of deaths have been recorded due to waterborne diseases, where more than 80% are children death. So most of them are cholera, malaria, hepatitis A, dysentery, and even typhoid. So which now brings us to the need of us having clean water. So what will now indicate that the water we drink or consume is safe? Most of the indicators are between these three classes, which are chemical, physical, and biological characteristics, where we will learn the turbidity of the water, the pH of the water, if the animals are able to survive in the water, if the water contains some microorganisms, microbes, algae, bacteria, as well as the like solids and other chemicals that may contaminate the water. So all of these characteristics are what we will base on to have a clean and safe water. So for the traditional techniques, there have been very tedious work. You cannot imagine now having thousands and millions of records of chemical, physical, and biological parameters that you will be recording on daily basis to know that people are able to have safe water. And this will include expensive equipments, laboratories, all the analysis that can be so expensive. So now we need a technique that can help us to be able to know if the water is safe, but at the same time, not tedious and cheap. So that's where artificial intelligence comes in, which have been now been used in many applications, either in health, environmental applications, in engineering applications. It has been nowadays been used, and it has shown high effectiveness. So this is where now we got our objective and methodology, where we will, in this study, we used support vector machine, random forest, k-near neighbors, logistic regression, ADA boost, and decision trees for the analysis of the water potability by considering 9 physicochemical parameters for water quality. So we have 9 physicochemical parameters, which are pH, hardness, solids, chloramines, sulfate, conductivity, organic carbon, trihalomethanes, and turbidity. So all the 9 parameters have been considered, where only 4 have shown high positive correlation with water potability, and 5 of them have shown negative correlation. So from the data that we got from Cargo, which is a publicly available data, with 3,276 records of the 9 physicochemical parameters. And now we trained these data sets where we used 80% of the data sets to train the models and 20% of the data sets to test the models. And the data sets were also grouped in 3 groups, whereby the first group was only physical characteristics, which included only turbidity, conductivity, and solids. The second group was only chemical characteristics, which included organic carbon, trihalomethanes, chloramines, sulfates, pH, and hardness. And now the third group included all the 9 features. So now from the training and testing of the models, the third group, which included all the 3 features, was found to have more precision recall index 1 score when being trained and tested in the models. Among the 6 models that were applied in this study, only decision tree was the one that did not have the high precision recall index 1 score for the group 3, but others have shown high results, which now brings out to a conclusion of the incorporation of both physical and chemical characteristics of water potability should be used to predict the potability of water instead of only using maybe physical characteristic or chemical characteristics, which were now group 1 and group 2. So it is better now to incorporate all possible characteristics, even though they have not shown that high correlation with the potability, but even in their lowest correlation, they were able to predict that water was either potable or not potable. So if we now have real-time data that we can use in incorporation with these machine learning models, we can surely now have cheaper and even faster, highly effective application of AI in water potability. Now, depending on the findings of this research, we can now be able to know the different water parameter data that can even influence the performance of the models. But this now have to highlight the need of knowing the data set you need and having as much as possible in their variability so that we can now be able to know how safe water can be so that we can prevent any health related issue that can arise from it. Thank you very much. If there is no question.
Thank you very much, Natasha. Thank you. Nice presentation. Now I would like to call Sahar to present the paper titled Synergies of Smart Sustainability. Yes.
Hello everyone, I'm Associate Professor Dr. Sahar Ebadinejad, and today I'm presenting the topic of synergies of the smart sustainability. And I present that for the third International Conference on Water Problem in the Mediterranean countries, and also the sixth International Conference on Natural Resource and Sustainable Environmental Management. The study aim is actually clarify how these components like AI, sustainable land management, and socio-environmental dynamic, they can actually influence and complement each other. So contributing to the holistic understanding and effective implementation of a sustainable water management practice in the context of the socio-environmental dynamic is very important. And in this conference, we want to get into that. So let's actually start with the introduction. Firstly, I would love to look at two different aspects in the introduction that I want to talk. Firstly, I want to talk about the importance of all of these components in the Mediterranean region. Actually, the importance of sustainable land management, AI, and socio-environmental dynamic in Mediterranean region, it lies in their collective impact on ecological health, resource conservations, and societal well-being. So sustainable land management, it actually ensures the preservation of the vital ecosystems, combating soil erosions, and it fostering the biodiversity. So integrating AI with these components, actually, as you see, it can enhance the efficiency in environmental monitoring, resource allocation, and also decision making. The second perspective that I would love to talk about, that is addressing the socio-environmental dynamic, which acknowledge the complex relationship between human activities and the environment, and promoting the harmonious coexistence here. So in the Mediterranean, where environmental challenges are pronounced, a holistic approach is very crucial for mitigating the climate change effect, protecting ecosystem, and securing resilience future for both nature and communities, of course. So I listed here some existing challenges, of course not all, but some of the existing challenges that we can name, that, like, for example, water scarcity. So we know that Mediterranean watershed, it often face water scarcity due to climate variability, due to the increasing demand of the water. And sustainable practices are definitely needed to manage the water resources much efficiently, ensuring availability for both ecosystem and human needs. Another challenge is soil erosion and degradation of that. So definitely implementing erosion control, that it can measure and it can promoting the sustainable agriculture, are very crucial for watershed sustainability. Another challenge is biodiversity loss. So conversion efforts and restoration projects, they are essential to protect the native species and protect and maintain the ecosystem resilience. Another challenge that I would love to mention about, that's the climate change impact. And as we know, the Mediterranean region is very vulnerable to climate change, leading to altered perceptions pattern and increase the temperature. That's why sustainable watershed management, it must be considered for climate adaptation strategies to can cope with this changing environmental condition. Another challenge that here I mentioned about it is land and sea interactions, also community engagement, policy and governance, and also resource use efficiency, because promoting the water and land use efficiency is very fundamental to sustainability. That's why employing the advanced technology and best practice, definitely it can optimize the resource utilization while it minimizing the environmental impact. So as you see, addressing these sustainability challenges, it actually requires a holistic approach, integrating ecological conservations, community involvement, and also policy initiatives. That's why collaboration between the stakeholders, including government, NGOs, and local communities, it's very crucial to ensure the long-term health and ensure the resilience of Mediterranean watershed. Now I would like to actually talk about the main key components here related to my topic and relevance of them to Mediterranean watershed. So AI, as you know, it enhances the water resource management, predict climate impacts, and is a great help in monitoring, in optimizing the agriculture practices, and it's very crucial in a water scarce Mediterranean region. Also, SLM, or sustainable land management, it mitigates soil erosions, promotes efficient water use, and also it preserves biodiversity. So that's why they are essential for sustainable ecosystems in vulnerable Mediterranean watershed, which, as you know, it facing with the land degradations and water scarcity. And another key component is the socio-environmental dynamic, which exactly recognize the local community's role, culture practice, governance in shaping the environmental outcome. As you see, it actually promote community engagement for sustainable watershed management in a Mediterranean context. So in the second perspective, I want to talk about the connection between them. So as we see here in Mediterranean watershed, AI, sustainable land management or SLM, and socio-environmental dynamic, they are interconnected components. AI, as you saw, it facilitated data-driven decision making in SLM, and actually it can addressing different kind of a challenge that identified through the understanding of a socio-environmental dynamics. So together, all of these components, they can offer a very comprehensive approach to can address the water scarcity, soil degradation, biodiversity loss, and climate vulnerability in Mediterranean watershed. And also together, integrating of them, definitely it can ensuring the balance between the ecological preservation and also societal needs. Now, I want to talk about smart sustainability from two different aspects. First of all, I want to actually talk about the role in addressing the environmental and social challenge in water management in the Mediterranean region. So, definitely, a smart sustainability, it can combine, as we said, technological innovation with a sustainable development objective, with offering a promising approach that can address the complex environmental and social challenge in the water management with the Mediterranean region. And by harnessing the power of the data and technology, and also the smart sustainability, as we see, it can contribute to the resilience, contributes to the long-term viability of the water resources and ecosystem in this crucial geographical area. In another perspective, actually, I brought different type of examples here that I would love to share with you. Definitely, these are some of the examples, but we have lots of examples. I don't want to put all of that in this conference. So, for example, the first examples I want to mention is a smart irrigation system. By implementing definitely the precision agriculture practice with a smart irrigation system, it can help to optimize the water usage in Mediterranean watershed. So as we see, these systems, they use sensors, they use data analytics to deliver the right amount of water to crops, to reducing the wastage, and to promoting the sustainable farming. Another example that I brought here is a water quality monitoring network. So we see that the smart sustainability initiative, it actually deployed the networks of a sensor to monitor the water quality in a real time. So definitely this can be, it can ensure the early detection of pollutions, enabling prompt interventions to actually maintain the health of the rivers, health of the coastal area in the Mediterranean. Another example is the integrated water management platform or community engagement application. We know that we have some different variety of smart application and platforms that they engage the local communities in a water conservation effort. And these innovatives, It actually raises awareness, provide education on a water saving practice, and it creates collaborative approach that can address the water challenge at the community level. And also flood prediction and early warning system is another type of a smart sustainability that it can be used here. So as the continuation, I would like to talk about the AI in water management. First of all, I want to look at it from the perspective of how it can enhance the data-driven decision making, and then we will look at how it can optimize the resource allocation and usage. So in the first perspective, which is enhancing the data-driven decision making, I can say that artificial intelligence it actually revolutionized the data-driven decision making in sustainable water management. How? By processing the extensive data sets from diverse sources. And we know that AI's analytical process, it actually identifies the pattern, identifies the trends, and also identify the correlation with these data sets and offering insights that are very crucial for informed decision making. Also, from other perspective, which is optimizing the resource allocation and usage of that, I can say that in actually sustainable water management, artificial intelligence emerge as a catalyst for optimizing the resource allocation and for usage. So through the machine learning, we know that AI system can analyze historical and real-time data accurately by predicting, for example, the future of a water demand. So you see that this predictive modeling is a great help in the judicious allocation of water resources, about how ensuring the efficiency of this distribution it can be. And also AI's impact extends to agriculture, where we know that a smart irrigation system, it can be driven by AI algorithm precisely by considering, for example, soil moisture or weather condition or crop water, how much crop water is needed. So we see that this precision, it can minimize the water wastage, reducing over irrigations and promoting the sustainable agriculture practice. And especially in an urban context, AI enhanced water distribution network by detecting anomalies and optimizing maintenance to conserve water resources and enhance the system resilience. So we see that the fusion of AI and sustainable water management, it actually heralds a paradigm that shifts toward the resource efficient practices. Also here, I would love to talk about interconnected synergies between the different components that we have. For example, AI informing sustainable water practices, one perspective that we can look at these synergies. We see that artificial intelligence, it actually enhances the sustainable water practice by analyzing the vast database, by predicting the demand, by optimizing the resource allocation. And a smart irrigation, it actually guided by AI in order to minimize the water wastage in agriculture, as you know. So that's why, as we see, this predictive analytics and real-time monitoring exactly empower the decision makers to proactively, they can address the water challenge, ensuring efficient and informed management of the water resources. Another perspective that we want to look at that is from the perspective of the socio-environmental consideration and decision making, which we know that in decision making, socio-environmental consideration are paramount. So this actually involves recognizing human nature interaction, understanding about societal impact on a water ecosystem, and fostering community engagement. That's why integrating this consideration, it can actually ensure holistic, ethical, and resilient water management strategy by addressing both environmental conservation and societal well-being, of course. And at the end, I would like to recap this conference here, my topic actually. And we see that by understanding the nexus and synergies between various components, such as artificial intelligence, sustainable water management, and socio-environmental dynamic, which are very crucial for developing informed and sustainable water management strategy. And these comprehensive components, these synergies combination, it actually enabling holistic approach. How? By integrating of a diverse element that can ensure comprehensive understanding of a water management challenge. Also, it enables optimization for decision making by identifying the synergies that allows for optimized decision making, utilizing the strength of each component. Also, it gives the capability of resilience, which exactly is recognizing the interconnection, builds resilience, enhancing the ability to adapt to changing environmental conditions. And it gives capability of balanced solution and also efficiency, which is very important because it maximizes the efficiency in the resource allocation, promoting judicious of use of the water resources here. So definitely, as we see in this sense, understanding the synergies and nexuses is kind of instrumental in crafting the strategies that are not only effective and efficient, but also is sustainable in the long term by ensuring the well-being of the ecosystem and community. Thank you very much, everyone, for attending to this conference and watching my presentation related to the paper that I had. Thank you so much. Bye, everyone.
Thank you very much, Sahar. Now we would like to call our third presenter, Dr. Huzaifa Umar, to present the paper titled Groundwater Quality Assessment. Thank you.
Good day, everyone. My name is Huzaifa Umar. Thank you so much for giving me the opportunity to participate in this third international conference on water problems in Mediterranean countries. I am here to present our studies titled Groundwater Quality Assessment based on physicochemical and microbiological parameters using advanced artificial intelligence models. This study was conducted with my fellow colleagues, Mubarak, Zubaida Mariam, and Professor Dilba Uzun. And it was conducted at the Operational Research Center in Healthcare. The main aim of this study was to determine the physicochemical and microbiological parameters of groundwater samples collected from Kano metropolitan cities. And we utilize artificial intelligence based models, support vector regression, random forest, XBoost, and CatBoost to predict the water quality parameters from our experimental data. And I'm going to present based on the following outlines: objectives, methodology, results, analysis, and finally conclusion. As you can see, actually, in this picture, actually there is a borehole, and there are children are trying to source water from that borehole. And actually, they are using that water for drinking purpose and other related activities. And in most developed countries, the groundwater is crucial resources for current and future generation. And if you can observe worldwide, the stress on freshwater from surface and ground sources is ever increasing due to high population and rapid industrialization. So natural occurring groundwater is typically of high quality, but it can be deteriorated or contaminated due to the insufficient source of protection and poor resource management. And sometimes this contamination might happen due to improper dwelling of wells and waste disposal. And the water actually is of great importance as we are using this water to carry out various activities. Our body also need this water to carry out metabolic and other related activities. And the stress on these water resources from the surface is increasing, as I said earlier, due to the population growth and rapid industrialization. So, this groundwater is much more reliable source of fresh water, which is under enormous pressure to fulfill the water demands for increasing global population, especially in developing countries, including our region, Africa. And the groundwater is found underground in the crack space in soil, sand, and rocks. And the groundwater also help to keep our rivers flowing. And it's also used for drinking by close to 50% of people in America and about 60 to 75 people in Africa. And the demand for this groundwater is of high at the moment due to domestic, agricultural, and other industrial purpose. But one of the most there is one important things that we should look. Some of this water actually contain organic and inorganic compounds. So these organic and inorganic compounds, they are either suspended or dissolved in the water. So they are determining the physicochemical parameters of this water will give us an insight on the organic and inorganic compounds present in the water, and also assessing the microbiological parameters, more especially like bacteria like E. coli, Shigella, and Salmonella, which are pathogenic, can also give us an insight on how to know the status of our water, of our groundwater. So the study objectives: monitoring and evaluating groundwater quality are crucial components of ineffective water resource management. So there is need for a constant monitoring and evaluating groundwater quality, so that to make sure that the water is of great quality and can be used for drinking purpose and other related activities. In our method, we actually carried out this study within Kano State metropolitan cities, in which we actually picked the samples from 3 urban cities, Gwale, Tarauni, and Nasarawa, and then from 2 peri-urban cities, Kumboso and Ungogo. And these samples were randomly collected using sterile 50 ml test tubes from boreholes located within the cities. And immediately after we took the samples, we carried out the pH analysis and recorded, and also the remaining samples, we took them to the lab to assess for electrical conductivity, salinity, chlorides, ion concentrations, sulfates concentrations and the rest. And also for the pH analysis, we use a digital pH meter. For the electrical conductivity, we use electrical conductivity measuring device. For the chloride ion, we use basic spectrophotometric analysis. And then these data, after we obtain them, we carried out modeling using artificial intelligence-based models, in which we use SBR, rainforest, XBoost, and CatBoost algorithm with Python to predict this data. And the data collected from experiments, actually, there are more than 200, and that they reveal the accuracy of the algorithms. And the result of the physicochemical analysis, we are also compared with WHO and National Environmental Quality Standards for drinking water, so that to see whether the groundwater can be used for drinking purpose. Actually, this is our result. As you can see, there is some abbreviation: G1, G2, T1, T2, off to U1, U2. Actually, these abbreviations, they stand for the G1 actually means the sample that was collected from borehole 1 in Gwale. The G2 means the sample that was collected in borehole 2. And as you can see, the pH actually is between 7.1 to 6.5, which is in accordance with WHO pH limit for drinking water, which is between 6.5 to 8.5. Also, the electrical conductivity of these water samples, as we can see, the samples within the 4 urban cities, they are higher when you compare it with the samples within the peri-urban cities, and that might be due to more activities within the co-urban cities. In addition, we measure the turbidity of the water samples, and also, as you can see, the water samples within the metropolitan, within the core metropolitan cities, actually is higher when you compare with those within the peri-urban cities. And also, sulfate ion was also tested. And ion also concentration was tested within the cities, as you can see here. And then we carried out, we trained our data using various AI-based models, in which actually, as you can see in these diagrams, the CatBoost training set and validation, the rainforest training set and validation was also shown. And we use MSE, MAE, and R-square as basic parameters to assess the performance of our models. And the R-square actually show more, actually, like the R-square actually is more good when you compare it with the other parameters that we use to assess the models. And based on our experimental, based on our data, the rainforest outperform the remaining artificial intelligence based models in both the training and validation stage, then followed by CatBoost, then followed by SBR, and then the XBoost. Furthermore, we carried out the antimicrobial analysis, in which we test for total coliform, Salmonella and Shigella, and also we use sterile water as our control. And in most of the local government, or in most of the cities, there is no any contamination, no any microbial contamination, but there are some actually in Gwale too. There are some Salmonella present, and in Terauni also there are some contamination, and which might be maybe due to the activities within the cities, since they are within the co-urban cities. Then in conclusion, our finding revealed that the majority of these piscochemical parameters in the metropolitan groundwater sources are within the WHO permissible limit, and they are free from bacterial contamination, assessed using total coliform and Salmonella and Shigella kits. And the AI-based models use SBR, RF, SG-Boost, and CAT-Boost, using our experimental data, show utmost performance in predicting the piscochemical parameters of our groundwater, and the rainforest outperformed the remaining artificial intelligence based models in both training and validation stage in terms of MSE and MAE. Albert Saint actually said, water is life's matter and matrix, mother and medium. There is no life without water. Thank you so much for listening, and thank you for giving me the opportunity to participate in this great conference. Thank you.
Thank you very much, Mr. Umar. Now I would like to call Dr. Professor Jawid Atal to present a paper titled Hydrological Characterization and Groundwater Potential Assessment.
Hello, good morning everyone. Thank you for being here today. My name is Abdulsalam Muhammad Saeed, and I'm postgraduate student here at Nrsem University, Department of Petroleum and Natural Gas Engineering. Today my title was Hydrogeological Characterization and Groundwater Potential Assessment. We explore groundwater. We take a geophysical survey to explore a subsurface. We use a geoelectrical method, special vertical electric sound method, and our study area was Sudan, special West Sudan area called Umdurman. This is our study area on a map. It's West Sudan. If you see left top map, this map is a Sudan map, and this is our study area, and this is the coordinate of the study area. To reach this area, it's so difficult, so we take 4-wheel driver car to reach this area. Also, to understand the topography of this study area, we take a topographic map. This is a contour map. It shows the topography of the study area. If you see the blue color represents the Nile River, and it's the lowest elevation, where the highest elevation represents this brown red color, and it's a mountain. And generally, this area is a flat area. Also, the climate of this area was affected by the desert, and mostly of the year is no rainfall. Average temperature area was 30 Celsius degree, and mostly of the year was above 20 Celsius degree. Sometimes it reached above 40 Celsius degree. Also, the average speed of the wind is 903 miles per hour, and this area also there is a humidity most of the year. Generally, this area is affected by the desert vegetation. Generally, this area is a lack of vegetation. However, there is a tendency of a small small trees called acacia. When we are there, we didn't see any other plants except this tree in the figure. If you see, this is a acacia tree. And it's a short tree. When we asked for the population of the area, they told us there is no other tree. The only plant that exists for this area, and it's called acacia. Generally, this area was affected by the deserting, so this is the only plant that exists for the area. Drainage system. The map of the left side shows the drainage system of the study area. The drainage system that exists in this area was a White Nile and River Nile, and there is a valleys. So this map shows the drainage system of. As we mentioned before, for this survey we use a geoelectrical method, and generally geoelectrical method is a method which conducts electricity to the east. If you see the diagram below, this figure shows how the geoelectrical method works. We conduct electricity to the east. We use 4 electrodes. 2 of them represent ampere or current. It reads, we conduct ammeter. It reads current. And 2 of them represent a voltage. There is different ways of arrangement of these electrodes, these 4 electrodes. One way is called vertical electric sound, which conducts this arrangement of the electrodes. 2 of them is current and 2 of them is a voltage. The outside 2 electrodes is current and the inside was a voltage. This way is called a phase or vertical electric sound. So we use for this arrangement which is called a vertical electric sound, and we take 15 phases in the survey. However, we only make analysis only 10 phases. When we conducted this electricity or these 4 electrodes, we use this above device which is called size 400. And this device, we take the readings. This reading was a resistivity, and each layer has a specific resistivity. So we take these readings and then we make analysis. We use an application called IB2E. This is the data we take from the field or from the survey. This data is the data we take from the readings of the device size 400. Each table represents 1 phase, and if you see the table, each table tells the coordinate of that phase or that station. So each table represents 1 phase, or each table represents the readings of that phase or that vertical electric sound readings. Totally, we make for the analysis 10 phases, and we take this data from the field. We make analysis. We use application called IB2E for the analysis, and this map shows the stations of that phases. It's 15 phases in the survey. Each star represents for the location of 1 phase. Totally, it's 15 phases in the survey. So each star represents 1 phase. Finally, when we use IB2E for the analysis, we get this output. The below figure is the output of the IB2E. If you see the line, blue line, each horizontal line represents 1 layer. This each first horizontal line was first layer, then the second horizontal line was a second layer. So totally it's 6 horizontal lines and 6 layers. First layer was superficial deposits. It starts from 0 top to 1.3 meter and a thickness of 1.3 meter. The resistivity of that layer was 162 meter. The second layer starts from 1.3 meter to 3.26 meter and thickness of 1.9 meter. The resistivity of that layer was very low, 40.6 meter. It seems that this is a clay. Third layer also starts from 3.26 to 5.38 and a thickness of 2.12 meter and it's a gravel. The fourth layer, it starts from 5.3 all the way to 58.2 meter and a thickness of 52.9 meter. The resistivity of that layer was 49 meter, and there is a presence of water in that layer. However, that water was salt water. Sixth layer was wet sand. I mean, a fifth layer is a wet sand. It starts from 58.2 meters to 141 meters and a thickness of 82 meters. The resistivity of that layer was so high, it's 923 ohm meter, and it's a siliceous sandstone. The last layer, or the sixth layer that appears for this output was the aquifer, and readings of that resistivity was 106 ohm meter. So this is the first phase. We will get each phase for different layers and different resistivity, and totally it's a 10 phase. So each phase it takes a long time, but this is the result of a phase 2, contains 7 layers. The sixth layer was the aquifer, starts from 69.7 meter to 440 meter, a thickness of 370 meter. It contains 7 layers for this phase. This is also a result of a phase 3. It contains 6 layers. The aquifer was the sixth layer, and the resistivity of the aquifer at that phase was 205 ohm meter. Also for phase 4, it contains 7 layers. The aquifer was the sixth layer. It started from 201 meter to 394 meter, and a thickness of 193 meter. The resistivity of the aquifer at that phase was 194 meter. For phase 5, it's a 6 layers. The aquifer was 6 layer, and resistivity of the aquifer was 100 ohm meter at phase 5. Phase 6 also contains 6 layers, and the aquifer was 6 layer, and resistivity of the aquifer at phase 6 was 164 ohm meter. For phase 7 also contains 6 layers, and the aquifer was 6 layer, and resistivity of the aquifer at phase 5 at phase 7 was 233 ohm meter. For phase 8, it contains 7 layers. The aquifer was the 7th layer, and it has a resistivity of 137 ohm meter. For phase 9, it contains 8 layers. The aquifer was the 7th layer, and it starts from 155 meters to 252 meters, a thickness of 96.2 meters. The resistivity of the aquifer at phase 9 was 205 ohm meters. Finally, phase 10 was the last phase for the analysis. It contains 7 layers. The aquifer was the 6th layer, starts from 56.8 meters to 461 meters, and the thickness of the aquifer at the phase 10 was 404 meters. And also the resistivity of the aquifer at phase 10 was 196 ohm meters. Also, IB2 gives you a pseudo suction profile, which gives you to demonstrate a color for your phases in a color way. The yellow color represents the aquifer. The best location for the drilling of the aquifer was a phase 10, which is the thickness of the aquifer at that location was so high. For the conclusion, totally this area contains 5 layers: superficial deposits, clay, sand, gravel, and siliceous sandstone. Clay is the layer with the lowest resistivity, between 2 ohm meter to 65 ohm meter. The productive zone of the aquifer was between 250 meters to 400 meters, and the aquifer resistivity was 180 to 230 ohm meter. This is the references. Finally, thank you everyone.
Thank you very much, Abdelrazak. Thank you for your presentation. Now I would like to end this session as we have no more presentation. Thank you very much for listening. See you next session. Now we have one more last video, which is going to be presented by Dr. Neda Jabus. Sorry, we have no more presentation. That's it for this session. Thank you very much for watching. Thank you very much for listening. And see you in next session. Thank you very much.
Hayat hızla akıyor ve biz bu hızı seviyoruz. Her güne heyecanla başlıyor, her anı doya doya yaşıyoruz. İlk günkü heyecanımızla yılları aşıyoruz. Zaman akarken biz de kendimizi arıyoruz. Heyecanla, merakla. Sen de kendini mi arıyorsun? O zaman zamana yetiş. Bu sadece kendini bulmakla ilgili değil. Asıl heyecan kendini yaratmakta. Bir şeyler mi yaratmak istiyorsun? Mükemmel. Metali işlemeyi, bir bina yapmayı, bir iş kurmayı, hatta bir şehir kurmayı öğren. Hayat kurtarmak, teknoloji geliştirmek, üretmek. Hepsi burada. Ve burada tüm deneyimler profesyonellerle yan yana. Ancak hızlı ilerlemeliyiz. Çünkü bugün şimdi gerçekleşiyor ve yarın çok yakın. Hayatta öne geçmek istiyorsan önce zamanın önüne geçeceksin. Hep ileri gideceksin. Bu Doktor Suat İrfan Günsel. Tanıyor musun? Onun da söylediği gibi. Üniversiteler toplumların dokuma tezgahıdır. Toplumları geliştirir, dönüştürür ve gelişmesini sağlar. O burayı bugünden yarına hazırlamak için kurdu. Senin için, ileriye gitmek için. Yana ya da geriye değil. Sadece ileri. Çünkü gelecek çok yakın. Hadi harekete geç. Fikirlerin ne kadar ileride olursa yarına o kadar yaklaşırsın. Yanındakileri de geleceğe taşırsın. Bu senin geleceğin, senin fırsatın şimdi. Hadi yarın yakın. Hepimizi ileriye götür.